In this video, we will talk about a couple of different memory technologies as well as the virtual memory system. So when you design the memory hierarchy of a computer, you have pretty much two different memory technologies to choose from. DRAMs, or Dynamic Random Access Memory, are designed to be able to store as large number of bits as possible, and it's implemented with just a single transistor per bit. But that implementation also comes with some shortcomings. One is that accessing DRAM is slow, and also that the data stored in DRAM sometimes can be changed by radiation. So rare occasions, a 1 can be turned into a 0, a 0 can be turned into 1. It's also quite complicated to implement DRAM systems. You have to deal with things called refresh and pre-charges in those implementations. We will not cover those in detail in this presentation. In order for you to be able to use DRAMs, you sometimes will have to complement them with what's called an error detection and correction technology. One such technology is ECC, to allow for you to make corrections to these bit flips that may happen in DRAMs. SRAMs, or static random access memories, are much more expensive to use. It requires between 4 and 6 transistors per bit. But on the other hand, they are much faster to access, and it's easier to make designs around the SRAMs. So here's a picture of what a DRAM looks like inside. So in this example, it's a 4 megabit DRAM, and the implementation is a mesh 2K by 2K to get the 4 megabits. And each intersection between the lines in the mesh is where you store the bits. So we see one such intersection here. We have the word line, and we have the column line here. And in the intersection, we have a single transistor, which is tied to a capacitor. And in this capacitor, you can store some charge. And if charge is stored there, that may mean that it's storing a 1. And if there is no charge stored there, then that could mean that it's storing a 0. When you address these kind of DRAMs, you do that in two different phases. First phase is you supply the raw address, and in the second phase, you supply the column address. So these are called RAS and CAS. Row address strobe, and CAS stands for column address strobe. So what's happening here is that you will supply the 8 bits of row address, which will be stored up here when you toggle the RAS signal. And these 11 bits will be used as an index function to uniquely identify one of these 2K rows. So one of these lines will be activated, and that means that the charge stored on all those 2K capacitors will now be able to be read out to this bit line here, or column line. So all the bits, the 2K bits stored in that line, will be read down here to the column latch. And as a second phase of this access, we will supply the second half of the address, also 11 bits, and they are used to select the data that we're interested in that was from out of those 2K bits. So this is sort of like a very wide multiplexer that's controlled by those bits. Since it is just a charge that's stored here, and there's some leakage going on, after a while that charge will be drained more and more. And if we didn't do anything special, that means that all the 1s and 0s stored in a DRAM would simply be lost after some period of time. There is something called a refresh, which means that you will go in and put in amplify the the charge stored on the capacitor. So you sort of read out if it was a 1 and 0 stored here, and then you will store back the same value, but with a higher higher charge, so which sort of remind the DRAM about what data you have stored it. And this has to be done periodically. And as we also already discussed, the bit error rate of DRAM is small, but still large enough that errors may be happening once in a while, and therefore we need to store some excess information in the DRAM so we can implement some kind of error detection and correction when one of these bits or a couple of the bits have flipped. DRAMs has another property which is that we leveraged when we designed the large cache lines. That property is that reading out the first piece of data from DRAM is slow, but reading out other data from the same line that we have accessed or right next to the first bit we read out can be done very quickly, so it can stream out the following data. There is one kind of DRAM called synchronous DRAM, or SDRAM for short, and an example of an SDRAM can be 5111 implementation running at 100 megahertz. That means that it takes 5 cycles to access the first data, and that the following cycles we will simply stream out the neighboring data, the following data in this example for another 3 cycles. So 1 long access and then 3 short accesses. The more common DRAMs right now are the DDR, that stands for double data rate DRAM. And here they work in a similar way. So in this example, 5, half, 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 that means that it still takes 5 cycles to get the first piece of data. And then in half a cycle, you read out the next data, half a cycle, the next data, and so on. We will look at some implementations later on in more detail. So here you have it. There are many different DRAM types. They have numbers, and the numbers refers to DDR, DDR2, DDR3. That refers to different generations of implementation of DDR, and the number after the dash relates to what frequency you can run the devices in. And here, for marketing reasons, they actually come up with the double frequency, the double clock rate that you will run these chips with, because they have a double data rate. So this is sort of the data rate. 300 megahertz is what you can read out data from that if you provide them with 150 megahertz clock. DRAMs, as you probably know, are organized on in units called a DIMM. So when you go in a store and buy DRAM, this is what it will look like. DIMM stands for Dual Inline Memory Module. And on one of these dual inline memory module, on both sides, you will have some number of DRAM chips. Often you have 8 on each side. So it's a total of 16 DRAM chips. In this example, the DIMM on the picture is a 2 gigabyte DIMM. So each of the 8 DRAM chips on this picture is a 128 megabyte chip. Inside that chip, you're going to have many of these meshes. In this example, you have 8 meshes inside that chip. And you will do this RAS and CAS and so on. That will happen internally on the chip at the mesh level. So there are 8 banks, and each one of those banks have this kind of mesh in it. I have a URL at the bottom of this slide, there where you can find more information at a quite nicely presented way in AnandTech. From that publication, you can also see different kind of detail of what happens when you access some data. So here is an example of a very fast kind of access to a DRAM, and this is when we actually access a piece of data that's already have been stored in the line buffer at the bottom of the chip. So at the top of the slide, you see how often the clock ticks. So this is between here and here is one clock cycle. Here's the next clock cycle, and so on. At this point in time, we provide the column address because we assume that we already have the correct row address, and the entire row has been read out. And this is when you can start to get the first data. So after a clock cycle number 6, you can start to get the data out. And as you can see, the data comes out at a double data rate. Data comes out twice, 2 pieces of data comes out in one clock cycle. So here's an example of a very fast access. Here's an example of a very slow access where it takes 18 cycles to get the first piece of data out. And what's happening here is we have some kind of pre-charge going on. We have row column. So we have to read out the line from the DRAM, and here we identify which column we're interested in, and that's where the data comes out. Finally, I would like to, before we leave memory technology, I would like to talk about what's referred to as the Endian Mess of memory. So we have the big endians and we have the little endians machines, and this actually refers to the book Gulliver's Travel. And Gulliver's Travel, he runs into some people who started a war, and the war was about whether you should open eggs on the pointy end or in the flat end of your egg. And so this war was between the big endians and the little endians. In the computer world, we also have two kinds of machines, and it's sort of almost the same as a silly kind of war going on as it was in Gulliver's, the book about Gulliver. And the war is about how you number bytes. Okay, so the big endian people says that that the most significant, so on the yellow box here is a word in a machine. We will assume here that the word is 4 bytes in this example. And the big endian people say that the most significant byte of that word should be numbered 0, and then 1, 2, 3, 4, 5, 6. So that's how they number the bytes in the memory. While the little endian people say that a word should be numbered starting with the least significant part. So they would enumerate the bytes 0, 1, 2, 3, 4, 5, 6, 7, and so on. So why is this a big deal? Well, if you store, for example, a number, let's say you would like to store the value, hex value 5F in the big endian and in the little endian machine, that means that they would store exactly the same thing. Because that's a least significant byte, and that's when you store the least significant bit of the data you store in both worlds. However, if you store a string, so for example the string hello, then the storage will start, the H will end up in the most significant part of the word, because that's where byte 0 is, while in the little endian world the H would end up in the least significant byte. So when you have byte addressable kind of applications, you really have to be aware of what's going on, and more importantly, when you port code between different architecture with different endianness, then you really have to understand what's going on. So much about different memory technologies. So SRAM, fast but costly. DRAM is much slower, but on the other hand, you can store much larger capacity if you use DRAM technology. What we're going to talk about now is the virtual memory system, and this is something that I'm sure you have covered in operating systems before, but I will give you the architecture view of what's going on in the virtual memory system. So if you haven't heard about the virtual memory system, your view would be that programs will generate physical addresses that uniquely identifies a piece of data in the DRAM, and that's sort of what we assumed when we discussed our how we implemented caches and so on. However, there are several reasons why you don't want to do this. First of all, if the program generates physical addresses and accesses DRAM directly, that means that the programmer will have to explicitly manage the contents of the DRAM. So the programmer would have to move chunks of data from the disk in the DRAM, work on it for a while, store the result back to disk, and so on. So that would be add extra complexity for the programmer. But it also means that the programmer must know how much physical memory you are going to have in the machine where you're going to run your application. And of course, that is often not the case, because the programmer may sit in the country somewhere far away and write the code, and he doesn't even know which generation of CPU that application will run on, and much less so how much memory you may have in your laptop at home. Also, if you need to manage the DRAM explicitly, that means it's going to be very hard for you to run several programs on your machine at the same time, or running several processes or several tasks and so on, because they may step on each other and overwrite the data that each one of them have been bringing into their special magic places in the DRAM. So instead, programs typically generate virtual addresses, at least when we talk about laptops or servers and that kind of computers. In the embedded world, it may be a different story. So what is a virtual address? Well, virtual address is actually a big fat lie. So the virtual address is a abstraction that we have told the compiler. So the abstraction is that, Mr. Compiler, we tell you that you own an address space which is 4 gigabytes large. Now just go ahead and use it. So 4 gigabytes large if you, for example, have a 32-bit addressable machine. But of course, that's a lie as good as any lie, because at this point in time, when you compile the code, we still typically don't know how large memory, physical memory, we will have in the machine where we're going to run that program. And this fat lie is told to all compilers, and all compilers, and also to all processes. So when you run a process, each process is going to be told that it has its own virtual address space. So here we have context A and context B, both of them believing that they have a full 32-bit address space that they can play around with. This address space is divided into segments. So in the text segment, you store instructions. In the data segment, you store static data. The stack is, of course, used to make procedure calls and so on. And the heap is where you allocate the data that is dynamically allocated by the program. So, for example, when you do malloc, that means that the data is going to end up on the heap. So the heap grows in one way, the stack grows in a different way, and when they collide in the middle, that means that you're going to crash and burn because you just run out of your virtual memory space. So given that the programs generate virtual addresses, so CPUs generate virtual addresses, that means we somewhere have to make a translation from the virtual world into the physical world. Otherwise, we don't know where the data resides. And of course, in that world, we know from previous lectures that we're going to have a cache hierarchy as well. But for now, we're going to skip the cache hierarchy and just look at how we access the physical memory. We're going to have an example here where we run two applications at the same time. And for simplicity, let's say that we are running ls, two instances of ls at the same time. Okay, so we're running the same application starting roughly at the same time. Application to the right, context B, will start a little before the context to the left. So context B will start to execute instructions, and so it will start to execute instructions. For example, in this red part of the virtual address is that I indicated here, which is a 4 kilobyte large virtual page. So first time you touch anything on that page, the operating system is going to say, whoops, you touched this piece of the virtual address space for the first time. I better try to figure out what's going on here. And the operating system says, I understand you would like to run ls, and I know that the code for ls that corresponds to these 4 kilobytes that you would like to access here, they actually reside at a certain place in disk. So what the operating system will do then is to create a or allocate a chunk in the physical memory which is 4 kilobytes large and say from now on, whenever context B wants to access its 4 kilobyte page down in the text segment, I will make sure that all those accesses are sent to this physical page of 4 kilobytes out in memory. The operating system will also, of course, bring in the data from disk where you stored the instructions for ls. Now execution goes on, and inside ls there is the first malloc happening. So now we want to allocate some space on the heap. Operating system jumps in and says, okay, I can give you a page frame in the physical memory. This is your page frame from now on. Whenever you like to read and write of those 4 kilobytes on your heap, I will make sure that those reads and stores will reads and writes will go to this physical page frame over here, and so on. The other context also starts to run ls, starting to run exactly the same instructions. Operating system will say, oi, now you touched this virtual address for the first time. Let me see what's going on here. Aha, you want to run ls, and actually I already mapped parts of those ls instructions into the physical memory. So I'm going to make sure that other context also will map to the same page frame of 4 kilobyte to start executing its instructions. Now the context A wants to grow its heap. So once more the operating system gets involved and says, when you would like to read and write to your heap, I'm going to create a completely different page frame for you, because of course these 2D instances of ls should not overwrite each other's data, dynamically allocated data spaces. So we get the fresh 4 kilobytes over here. Also, when the operating system does this, it will put some kind of protection or access rights associated with each one of these mappings. So for the instructions, you will only be able to read the instructions. You're not allowed to overwrite this piece of memory. Or maybe it's just an execute privilege you have. You can only execute these instructions. While the heap, each of the context gets both read and write permission, but can, on the other hand, not access each other's heap places, so they cannot destroy for each other. So here's the question. One way to view the virtual memory system is to say that what we've implemented here is simply we turned the DRAM into a cache. The DRAM caches data from the disk. Okay, so if you look at this virtual memory system as just a way to implement a disk cache, then how large would you say that its cache lines are? And since data is moved in 4 kilobyte chunks from the disk, and the allocation of space is done in 4 kilobyte chunks, the right answer is 4 kilobyte is what corresponds to cache line in the cache implementation. So a virtual memory system is like a cache, and just like the virtual memory system cache implementation, we just like other cache implementations, we need to understand where to place a specific cache line, where a specific cache line can be placed in memory. Okay, so let's give an example. In a 4-way set associative cache, there were each cache line had 4 possible locations where it could reside, and it was up to the cache allocation algorithm backed by LRU, replacement strategies, and so on, that decided which of these 4 places should be used for a specific cache line. But what is the organization of a virtual memory system? For one of its cache lines, so one of its 4 kilobyte pages, what are the placement restrictions? How many different places can we choose between when we bring a 4 kilobyte page into memory? In other words, what is the associativity of the virtual memory system? So a page that's brought in from disk can actually occupy any page frame in DRAM. So look, comparing this to the cache implementations we had before, there is no index function here, okay? Which means that it's actually a fully associative cache. So the virtual memory system turns the DRAM into a fully associative cache, okay? Sometimes there could be some restrictions that has to do with page coloring, but I just leave that as a side note now that the operating system can actually imply some other restrictions as well. But at the general level, it looks like a fully associative cache. So a fully associative cache, does that mean that we now have to have many, to do many compares in parallel, and we have to make address tags comparisons in order for us to implement this fully associative cache? Well, that is actually, fortunately, not the case. Instead, we implement the mapping of virtual addresses to physical addresses. It is done through a large table. So we have a page table, and that page table lives in main memory. And what you do when you like to make translation from a virtual address to physical address is that you simply index into that table, and on using the most significant part of the virtual address, and that will enable you to read out the corresponding page table entry that corresponds to that virtual page frame, and that will contain pointer to the physical address that you need in memory. So the most significant part of your address are translated through this page table entry in this page table to get the most significant part of the physical address. The least significant part of the address will not change when you go from virtual to physical, because all these 4K page frames are aligned both in the virtual world and in the physical world. So for a 4K kilobyte large page, the 12 least significant bits of the address will not change. But there are a couple of problems actually with this table scheme. One problem is that the size of this table needs to be enormously large. So in modern computer systems, we have an address space of at least 48 bits or so. And if you do the calculation, assume that we have a 48 virtual address bit space, and you see that for each 4 kilobyte page, you need one of these page table entries. Assume that each of these entries is about 4 bytes large. If you do the math, you can quickly come up with a number that this table needs to be 256 gigabytes. And that clearly is not practical. And this can't live on disk, it has to live in memory, right? Because this is the table that's going to help us access the physical addresses here. So there are a couple of solutions. One observation first is that this table that I've showed you here that's so large, it has one entry for each possible virtual address that you can access. While actually for this translation to work, the only requirement is that we have one entry per physical page. We only need to have these kind of mappings for the data that lives in the physical memory, not for the entire disk. Okay. One implementation that relies on that is what's called multi-level page table. We're going to talk about on the next slide. Another way to implement this kind of table in a more effective way is to do what's called an inverted page table or a hashing table. And both of these techniques, they leverage the fact that we only need translations for data that actually is in physical memory, not for the entire virtual address space. So here's an example from the alpha architecture, where how you implement a multi-level page table entry translation. So first, at the top we have the virtual address. So these are 48 bits or so of virtual address. We divide that address into different chunks. So the blue chunk, red chunk, green chunk, and the purple chunk. So some number of bits in each one, so 10, 11 or so bits in each one of these chunks. The process, each process executing in the machine has some kind of state associated with it, and one of important piece of information is the page table base register that points to a physical page in memory. So what we're going to do here is we're going to take these 10 or 11 bits here of this part of the address, and we're going to use them to index into this page table to read one of the 1,000 entries out here, and then we get what's stored in that location is a pointer to another physical page frame. There's another 4. Actually, in case of the alpha, the page size was 8 kilobytes, but it's some number of kilobyte page, and then we use the red bits to index into that page to get a pointer to another physical page frame. We use the green bits to index into that page frame, and this is where the page table entry resides. So this way you will have the translations from virtual to physical, as well as the protection bits, necessary protection bits. So we're going to have the physical page frame stored here, so that is going to be part of the physical address, and then we're going to take the purple bits at the least significant part of the bits of the virtual address and just simply tag them on at the least significant part of the physical address to create that address. So now we have the physical address. Now we can actually access the DRAM. As we already discussed before, there are some protection mechanisms implemented jointly with this whole translation mechanism. So we have some protection attribute bits for each page, okay? And these attribute bits are stored in the page table entry together with the translation. And it's interesting to note here that different processes may have different protection bits for the very same page. So one process may have read and write access while another process may only have read access or no access at all to a specific page. If you make a violation, so if you try to make an access that the protection says you're not allowed to do, if you try to modify a page that you're not allowed to modify, you will cause an exception, which is called a trap. This may not necessarily be an error, because there are some schemes, for example, copy on write is a scheme that leverages these kind of protection and software traps to implement a very fast way of doing forks in Unix, for example. You also have a supervisor mode. So it's easy to understand here that if you can go in and change some critical data structures from user level, for example, if you go in and change the page table entries themselves, you could completely destroy the security of your system, as well as destroying the functionality of other programs. So that is also part of this page table entry. Okay, so we talked about how to make a translation from a virtual address to a physical address, and it looks like we can do it with using a reasonable size table. Problem though is that if you're going to do that translation, the page, what's called the table walk to make the translation, that means that we will need to do 3 extra memory references each time we would like to touch some piece of memory to access some data. That doesn't look very effective. The solution to this is the solution you see many times before. We introduce a caching mechanism. So what we're going to do now is to introduce a new kind of cache, which is called Translation Look-Aside Buffer, TLB for short, which is a pretty bad historic name. I think that just calling it an address translation cache would have been much better, for example. So we have an architecture, simplified architecture, when you show that the processor, the CPU, will generate a virtual address. That virtual address is sent to this TLB, which is the cache, where we quickly can do a lookup where we store the most recently used translations from virtual to physical. And if you're lucky, then the TLB will contain the translation we're looking for, which means that it quickly can produce a physical address. Now we can start to access our first level cache or access the memory, the main memory system. If the TLB does not contain the translation we're interested in, then we will have to go or do the table walk to do the costly translation to produce the physical address. But once we have done that costly translation once to produce the physical address, then we can also store this translation in the TLB, and maybe we can leverage that later on. So this is much better. We don't have to make 3 memory references each time we would like to read a piece of data. Instead, we can just go and do a cache lookup to go from virtual to physical. And once we have the result of that cache lookup, then is the point in time where we can start to access our cache. But still, we have put some extra work on the critical path. So we spent quite a lot of time understanding how to make very fast caches, and now we added some extra translation mechanism on the critical path to that cache. That doesn't look pretty. Question is, do we really need to do a TLB lookup for every L1 access? Okay, or could we do something different? Why can we not implement a cache, a first level cache, where we call data by their virtual addresses instead of naming them using their physical addresses? So it's just a matter of what we call things in the different spaces. So we can, by doing that, we could actually move the TLB to the other side of the cache and put it off the critical path. So here we see such a design. We have the cache close to the processor now. It has virtual address tags, so we speak virtual addresses when we speak to that cache. If we miss in the cache, then we need to go to the address translation before we go to memory, because we only need to know the physical address when we actually are going to access the DRAM location, the very DRAM location where that data resides. This means that the TLB can be much larger and potentially much slower, while we can still run our applications very fast, because as long as we stay in the cache world, we can enjoy a short access time. We know TLB accesses on the critical path. However, are there any problems with such virtual caches? Would this system even work? There are a couple of problems, and we refer to those problems as aliasing problem and homonym problems. So the way you use the virtual address space allow you, for example, to have the same physical page can be accessed using many different virtual addresses. Okay, so for example, you could imagine 2 processes that each internally use different virtual addresses, and those virtual addresses have been set up to point to the same physical page. It's also actually okay for one process to have several different virtual addresses pointing to the very same place. So this is called the aliasing problem. We can have lots of different virtual names for the same physical place in memory. And the other thing also, the opposite also holds, that we can actually have different physical addresses. Different physical addresses may be referred to by the same virtual address, and we saw an example of that in this ls example on the heap. So both those instances of ls use the same virtual addresses to access their part of the heap, but the mapping was actually to different physical pages, so that's called homonyms. And there can be lots of confusion here. So if you have aliasing and use virtual caches, that means that the same piece of data may exist in the cache at the same time using different aliasing. So under different virtual names, it could reside, many copies of the same piece of data could reside in the cache. And this could really confuse the computation. Let's say that one of those locations may be changed, the value of that location may be changed, while that means that processes or programs accessing any of the other aliasing would not see the newly changed value. There are some techniques you can do. You can, for example, try to flush the cache each time you switch processes, but that only solves some of these problems. So what we're going to talk about here instead is a solution which is called the virtually indexed, physically tagged cache. And that is a cache which you can access quickly, but it does not have this aliasing problem. Later on in this cache, I'm going to discuss other solutions, how to handle synonyms, and we have actually we're just about to publish a paper for some of the research we've done here. We have a very fast tagless cache implementation, which is actually a virtual cache that handles these synonyms. This is work that Andreas has done, and in about a month or so, I will share some of those results with you. But now we're talking about virtually indexed, physically tagged cache as one way of removing the TLB lookup from the critical path. What you have here is a slightly different design than the previous two designs we have seen. Here, instead of putting the TLB before or putting it after the cache, we put it in parallel with the cache. So here we have a cache, and this cache has physical address tags. The processor will produce a virtual address, and we will use this virtual address, some of the bits of this virtual address, we will use that to index into the cache. And if we make this cache small enough, or if the other way to put it is, if the index bits that we need here are the least significant bits, those bits that will not change when we go from a virtual address to a physical address, then we can actually use the virtual address to index into our cache. At the same time as we access the cache, we also start to do the lookup of the TLB, and we assume that the TLB and the cache has about the same access time. After a while, the address tag comes out from the cache, and about the same time, the physical address will come out with the TLB. That means we can actually do the comparison exactly at the same point in time we did in our previous cache designs. So here we can determine if it is a hit or not, and if it's not a hit, then we take the physical address and we go to main memory. So this is a way for us to actually remove the TLB from the critical path, but still implement a system where we have physical tags. However, in order for this to work, we have to guarantee that all aliases have the same index function. So if there are many aliases, only one of them can reside in the cache, and that means that they all have to index to the same location. And if there is another alias in the cache, that means that when we do a lookup, we will get a match from whether the physical address tag, because the physical tag is the same for all the different aliases of this specific cache line. So in order for us to guarantee that, we have to make sure that the cache size of a VIPT cache is smaller than or equal to the page size times the associativity. Okay, which means only this implies that only the bits that don't change when you go to from virtual to physical addresses, only those bits are used to index the cache, if this invariance holds here. There is another technique called page coloring, we mentioned before, and if you have an operating system that uses page coloring, you can this restriction can be lowered a little bit, so you can actually make larger cache sizes for a given associativity. But that is something we'll not cover in detail in this course. So putting it all together, let's look at what this VIPT cache looks like at the same level of detail we looked at caches before. So we're going to implement a 8 kilobyte two-way set associative cache. Cache line size is 32 bytes in this example. Word size is 4 bytes, and the page size is 4 kilobytes. We're also going to have a TLB, the translation cache, and that TLB has 32 entries, and it's a two-way set associative cache in this example. So the cache here looks like the cache we implemented before. It's a two-way set associative cache. So either the cache line we're looking for resides in the left side or the right-hand side. We're reading out 32 bytes here. We have some kind of multiplexer that will make sure we return the left or the right, and also will make sure that we are returning the 4 bytes that the CPU asked for, not the entire 32 byte cache line. We have 128 entries in this cache. So putting the design together here, we throw away the two least significant bits because they identify a byte within a word, so word size 4 bytes. We have the next 3 bits that's going to drive this multiplexer somehow. And the next 7 bits we're going to use to index into the cache because it's 128 entries in this cache. It's interesting to note now that these are exactly the 12 bits that don't change when we go from a virtual address to a physical address, given that the page size is 4 kilobytes. And this is not just pure luck, it's really by design. This is something that has to hold for the VIPT cache to work. We store a physical address tag on these two places. So we're going to store a 20-bit address tag because we have 20 bits that we didn't use for this lookup. The TLB is also a cache, and the cache stores a page table entry in its data space. Okay, and then it stores some virtual tag and a valid bit, of course. So the page table entry will store the translation of the virtual to physical translation for the 20 most significant bit. The bits they're going to change when we go from virtual to physical. We have 16 entries, 16 different entries in this cache of 16 different sets. So that means we're going to use 4 bits to index into the cache, and which means we're going to have a virtual address tag of 16 bits, and those 16 bits will be compared with the most significant 16 bits of the virtual address. If it's a hit in any of these ways, the logic will choose the left or the right address translation, depending on which one matched. So here we will have the physical address bits 31 through 12. Those bits going to be compared with these 20 address tag bits stored up here and the 20 bits stored there. The logic will choose left or right, and that will help us determine, drive the multiplexer. So we can have the left and right information as well as these 3 bits that will identify a word within a cache line to drive this mux. And so this is the entire design. Now the question is, given that you have seen this design now, can you answer this question? If you want to make a 128 kilobyte L1 VIPT cache for a x86 system, assuming the page size is 4 kilobyte, not just 4K as it says here, what's the minimum associativity needed for this VIPT cache to work? And of course, a hint to that solution was in the previous slide that we said the VIPT cache size must be smaller than or equal to the page size times the associativity. So you actually need the associativity to be 32-way associative cache, which is probably on the high-end side from an energy point of view. So lastly, we're going to talk about the capacity of the TLB. So a TLB, the size of that cache itself probably is maybe half a kilobyte to a 2 kilobyte. They are fairly small because they have to be accessed very, very quickly. Each translation entry is, it maybe holds the PTE, page table entries, like maybe 4 bytes or maybe 8 bytes, depending on how much protection and things you have in there. So that means that given these size caches, you will get between 32 and 512 entries, TLB entries, or different address translations that can be stored at the same time. Typical page size is, let's say, 4 kilobytes, or sometimes a little larger, so maybe between 4 kilobytes and 16 kilobytes. That means that the TLB reach of this cache design, if you have 32 entries and you multiply how large data capacity that those 32 pages for which we have the translation in the TLB, what data capacity can they use, you come to about 0.1 megabyte of data that can be translated using these 32 entries. On the high end, 512 entries times the larger pages, you would end up with the TLB reach being 8 megabytes instead. This is a little bit of a problem because, as we already seen, TLB miss can be very costly and maybe sometimes require several lookups in tables and several DRAM accesses. So this kind of reach is not satisfactory for many applications. And also typically you do want the TLB reach which is larger than the cache size you're accessing, because TLB miss is more costly than the cache miss. So otherwise you are spending your transistors in the wrong place. So there are a couple of fixes to the problem with the TLB reach. One is that you can use multiple page sizes. For example, you may have pages that are 4 kilobytes or pages that are 1 megabyte in your design, and the operating system can choose which one to use. So if you're going to make a translation, let's say you have a large matrix and that you would like to access. So when you allocate that enormous matrix, the operating system can say, look at this, it's a large chunk of data. Instead for me to use small 4K kilobyte pages to map this entire matrix, maybe I should use 8 megabyte pages. That means that each entry in my TLB can now contain a translation for this super page holding 4 megabytes of information. So this is very common in operating systems that you leverage these kind of large pages. Well, another example where you use that is when you map the operating system itself and many of the data structures that the operating system needs to access using large pages is a good idea. So typically you have a mix of different page sizes that are supported by the TLB and by the operating system. Another fairly common trick these days is to have a hierarchy of TLBs. So you have a TLB 1, first level TLB. That's the one we've been looking at in this design. So this data TLB1, and then you can have a second level TLB, which is much larger, but also slightly slower, and so on. So you make these kind of TLB designs, make them sort of match the different cache sizes and speeds of different levels in the cache hierarchy by itself. So we already talked about the placement of pages in the virtual memory system, and we noticed that the organization of the virtual memory is like a fully associative cache. If we go back to this cache analogy and we ask ourselves what kind of page replacement policies can we use? Well, we could, for example, do we want to use least recently used page replacement eviction when we decide which page to throw out of the DRAM when we run out of space? That wouldn't be very practical. So the more popular page replacement strategy is used is FIFO, first in, first out. That's you simply take the page that's been living in the memory the longest and you throw that one out. Or you can do some approximation of LRU. So it's very common that you, for example, in the page table entry, you have a specific reference bit that says whether or not this page has been accessed recently. And whenever you access a page, if that bit is not set, then you will automatically set that bit in the TLB, and eventually also write that kind of information back to the page table in memory. So with that, if you periodically go, the operating system will reset these reference bits, and then it can figure out which pages are actively being used right now, and make sure that you don't throw out any of the more recently used pages. So that it's a way to, using this reference bit, you can actually approximate LRU to some extent. So what write strategy would you use for this cache, the virtual memory system? Write back or write through? Write back. There is no one trying to do a write through, because if you had a write through cache, that means that every time you made a small modification to words or bytes, you would have to write those changes all the way out to disk, and at least you would have to do a cache line granularity writes, and disks are not well suited for doing small writes. They are much better at writing big chunks like pages and so on. So you use write back, and you have a dirty bit associated with the page table entry for each page, and you set that bit the first time you write to the page, and it's a sticky bit. And when you need to throw out that page, if the bit is set, well, you need to write back the information to the disk. So finally, if we compare the virtual memory system, if you look at it, if you compare it to a cache, we look at the virtual memory system as a cache, and we try to map the kind of features we have in the virtual memory system to the cache language that we used before. So we had the virtual address, and that address is the address that we used in our drawings of the caches, so it's a cache address. Okay. The physical address corresponds to cache location. Okay, so physical address uniquely identify exactly where in the cache the data resides. So in this example, in a 4-way set associative cache, you would not only know the index function, you would also know which of the 4 ways the data you're looking for resides. That information, that's what the physical address can do for you in the DRAM world. A page, well, it's a huge cache block or cache line. They're 2 names for the same thing. Page fault, that's an extremely painful cache miss, where you have to go out and bring in some data from disk. You access a page which is not in the physical memory, you have to bring it out from the disk. Page fault handler is the software that fills the DRAM with the data. And page out in the virtual memory world, that is when you just toss a page over your shoulder, or you have to write it back if it's dirty.